We're going to take another look at solids of revolution. So a solid of revolution is just when you take a graph and wrap it around a certain line to create a solid of revolution. So if what we have here is a guy named Michael Cooper created this Geogebra Applet, and it's going to demonstrate what we're trying to do here. So up until now, we've done disks or washers to help us find the volume of a solid. So if we take a look here, if we took this graph, so let's just take a look at what we have here. If you look here at the top, it says function to rotate 1/8 x squared. So there's a parabola, 1/8 x squared, and it's going from 1.4 to 5.6, just some random values there. And right now there's 11 sub-intervals. So it's splitting this thing into 11 parts. And then, as we saw earlier, and I'll go back again, so here's on the right, you can see another graph of this, but it's going to show some 3D stuff here. So if we rotate this around the y-axis, we notice we have this solid of revolution. Now we could use the washer method or disk method, which you do the outer layer minus the inner layer to find the volume of this. But we're going to have a new method here, and it's called shells. And so other times it's called layers. But what we're going to do is we're going to look at each of these rectangles here. So I'm going to start back over. You notice there's these, when we split it in here, we have these 3 rectangles, and these 11 rectangles, and we're going to wrap those rectangles around the y-axis. And if we were able to find the volume of those shapes that get wrapped around, we would be able to closer and closer estimate the volume of this solid of revolution. So we're going to go ahead and wrap this around. I'm going to stop about right here because over on the right side you see each of the 11 rectangles being wrapped around, and that's going to help us find our volume. So what we are going to do here is we're going to take each of those rectangles that's wrapped around and realize those can be unwrapped, and you would simply have a rectangular prism. So we can find the volume of each of those rectangular prisms. I'm going to go ahead and take a screenshot of this. And I want to go ahead and draw on it here for a little bit. So as we look at, let's look at this outer rectangle here, which is right here, and that could be wrapped all the way around. And if you would think about that as if we unwrap that, we would have this large rectangular prism that's not very deep at all. It's actually the thickness of this rectangle right here. And we could find the volume of that rectangular prism. And then we could find the volume of the next one. So the volume as we look at this one wrapped around, which is the second one in here. And then we could do the third one. And we could do all 11 of them, and we could add those together to get an approximate volume. Now we learned that instead of doing all these little rectangles, we can use integration. And so that's what we're going to end up doing here. But let's take a look at what we're actually finding. We'll integrate in order to add up kind of all those rectangular prisms, like this blue one here. So let's find the volume of this rectangular prism. Well, the volume, this is going to be length times width times height. So this length here, if you think about that, that represents, I'm going to have a tough time drawing this probably, but that represents this value here, which is actually the circumference of the circle. So that's going to be 2 pi times the radius, and we'll have to think about what that radius is in a few minutes. And then we're going to find the width. Well, the width of this is just this change in x value, so that's going to be dx. And then the height is this value here, and we actually think about, well, that's the height of the function at that spot, which is the y value. And so our volume of this thing is going to be 2 times pi. Well, the radius is just our x value. So that's x. And then y dx, so I'm switching the order a little bit. Dx is going here, y is going here. But we actually know up here what y is equal to. Y is equal to 1/8 x squared. So as we look at this, the volume is going to be 2 pi r, which is x, times the height of the function, which this is f of x, or whatever function we're talking about, y, and then dx. So in this case, we know the function, and so we'll be able to use that function in different situations. We'll have different functions, but it's going to be 2 pi x times 1/8 x squared dx. That's the volume of one of these rectangular prisms that gets wrapped out, one of these shells or layers. And so we just peel off shell by shell, and we can find the volume. And so what we'll realize is we can take the integral of 2 pi x times the function that's being rotated around the x-axis, dx, and we would have from a to b. In this case, a and b would be the 1.4 and the 5.6. And that's how we can find the volume of a solid of revolution using this shells method.